3.5 discusses limits at infinity. This is a concept that you have seen before in Algebra 2 and Pre-Cal, but we're going to deal with it this time rather than using just rules like you learned in Algebra 2 and Pre-Cal. We're going to learn to deal with it as a limit. Since we've dealt with limits now, we can kind of go back and use that information to deal with these asymptotes. Really what we're talking about with a limit at infinity or horizontal asymptote, sometimes called end behavior, is what is happening to the function itself, or the value of the function, as our x value becomes very large in the negative direction, so it approaches negative infinity, or our x value becomes very large in the positive direction, so we're approaching positive infinity. And just as a note, as we work through these problems, we'll see in a few different places that a function can have at most two horizontal asymptotes. It could have one to the right and one to the left. In other words, one as we approach negative infinity and one as we approach positive infinity. That hasn't probably been true for the problems that you've seen in Algebra 2 and Pre-Cal, but we'll see how there's some that come up now that we understand this idea of limits that we can deal with in calculus that we couldn't deal with before. And also, just kind of as a quick reminder, remember that anytime we have a number over a denominator that's approaching infinity or negative infinity, so we have a finite value over a infinity or positive infinity or negative infinity, that the overall value of that fraction is going to approach 0. So we're going to talk first about horizontal asymptotes for rational functions, and these are the types you've seen before in either Algebra 2 or Pre-Cal, probably both. And you probably learned 3 different rules for this type of, or for a horizontal asymptote with this type of function. Sometimes students learn the Bobo-Botten eats DC, and kind of as a mnemonic for those 3 rules. A rational function will have at most one horizontal asymptote. So these are the types you've seen before, so they're kind of typical horizontal asymptotes. But the way that we're going to deal with them now is, rather than memorizing rules, we're going to treat them as a limit. So we have a function 3 minus 5 over x squared, and we're trying to figure out what the limit at infinity is, or what the horizontal asymptote is, or what the end behavior is. It could be worded any of those ways. We're going to take the limit as x approaches infinity of that function. And of course 3 doesn't depend upon x, so it stays a 3, but our denominator here approaches infinity squared, and so 5 over infinity squared approaches 3, and we can see that the horizontal asymptote there is going to be y equals 3. So that's one that we really just do by substitution. We're going to see this next example, 2x minus 1 over x plus 1. When we look at a limit at infinity for that function, if we just try to use substitution, which we always want to do for a limit, if you recall from back at the beginning of the year, any type of a limit, we want to start off trying just solving it by substitution. Here we get infinity over infinity, which is another indeterminate form, so we have to change the way this looks. And the way that we're always going to approach this, anytime we get infinity over infinity, we're going to divide by the highest power of x anywhere in the rational function. Okay, so as we look through this problem, we have an x to the first up here and an x to the first down here. So x to the first is the highest power of x, and so we're going to divide the entire numerator by x and the entire denominator by x. Alright, so just like we can multiply numerator and denominator by anything, we can also divide the numerator and denominator by anything. And in fact, really, you could think of this as we're multiplying the numerator by 1 over x, and we're multiplying the denominator by 1 over x. So when we do that, you'll see we're going to get something that looks a lot more like the first problem we did up above. So when we divide everything by x, the 2x divided by x gives us a 2. The x divided by x gives us a 1. But now we have x's in the denominators of both the numerator and the denominator. So the 2 remains a 2 by substitution, and the 1 remains a 1, but when we substitute that infinity into the denominator here, we get a 0. When we substitute the infinity into this x in the denominator here, we get a 0, so we are just left with 2 over 1, and so the limit as x approaches infinity of this 2x minus 1 over x plus 1 is just 2.